And now we're going to move on with our second demo, which is a use case from University of Washington. So I will ask Professor Jeff Bond to come up here and take us through.
Thank you, Greg. Very nice to be here, and I'd like to thank Mcity and University of Washington, and also ISF for making this happen, and also thanks for the nice weather today. Yeah, so always like this. I know, I like Seattle, you know. I'm also honored to present the second demo on the multi-scale traffic control with connected and autonomous vehicles. I think the organizers changed the lead slightly to joint control of AVs and traffic signals. I actually like that better, so I'm going to use that. I think I can use this. So I'd like to introduce the team a little bit. So I've been very fortunate to work with two excellent students. Dr. Changcheng Guo has been working on this, and this is mainly his dissertation research, and he developed most of the models and computer code. And he graduated a couple years ago and now working in industry. And Sakiba has been working with the lab for the last 3 years as a PhD student. And she kind of redeveloped part of the model and the programs in order to integrate with Mcity interface. I also briefly introduced my lab, Intelligent Urban Transportation Systems research. So we do data-related work. You know, today, you know, who doesn't work on data, right? So, we try to use data to inform transportation modeling, especially try to look at what the AVs brought to infrastructure and how to cooperate AVs and transportation infrastructure, such as traffic signals. And we try to reformulate things as so-called multi-scale control, because if you look at large urban transportation systems, it's indeed multi-scale from vehicles to traffic lights, corridors, and networks, you know, infrastructure. So, today we're going to focus on this so-called intersection and vehicle, or the joint control of the two systems. So this is where we publish the work. So then, as a researcher, right? So I've been working on CV-related research, particularly from the infrastructure side. I think the pain points are really the lack of real testing facilities. So, like my student I mentioned, his dissertation is mainly in simulation and limited real data. And so it's hard to evaluate how the performance of these control algorithms in a mixed environment, you know, large-scale systems, in a real, you know, traffic systems, and how to interact with a real infrastructure. So today, if you have 1 or 2 AVs in a research lab, that's already great. But if you try to control the traffic lights on the streets, that's really hard, right? So not to mention you try to control both. There are testing facilities in the past, including Mcity, but really hard for researchers to access. You have to come here physically. You know, transport your car from Seattle to here, I cannot imagine how much you need to pay, right? So I think the real kind of innovation of Mcity 2.0 is to have this remote access capability, really the game changer. I think Henry already mentioned how the system works. So this is from our, you know, researcher point of view, how we work with Mcity, the remote interface. So here, oops, sorry. So from our side, we can access from the TerraSim, the Mcity, like the map, the signal status, vehicle status through cloud to the remote access. And on our side, we develop our vehicle signal control algorithms and how to make them consistent and algorithms to solve it. And then this algorithm will sort of feed back to Mcity to run either simulation or the mixed reality testing. And the results can be visualized through different visualizers, the cameras, you know, the dashboard, and the real-time performance, so on and so forth. So briefly about what we did. So we picked one intersection, as you can see from here. It's with the real world traffic lights, traffic control systems. And we tested in the mixed reality testing, we did 100% CUVs, like all the cars, including the background vehicles, are CUVs. But in simulation, we tested different penetration rates to look at the mixed environment performance. So some of the challenges during the integration or development is really the real kind of real world kind of scenarios, because when we do simulation, we have some ideal assumptions regarding, for example, how long the incoming road should be long enough so that you don't interact with other traffic lights. But here, you can see it's very closely spaced. So you have to adapt your algorithms for that, and also you have to adapt things to consider real traffic operations like the minimum green, this kind of parameters. But you can see with Mcity engineers' help, we were able to successfully did the integration and also the testing. So there will be a live demo after this, so I'm not going to go into the details here. Well, so far it's fun, right, to do the integration, to do research, but as a researcher, we want to know, does this work, right? How the performance look like? And here you can see the 100% penetration case. I guess the figure probably too small, but I wanted to sort of indicate is there's 6 figures, but 3 bars on each figure on the left side. So the bar indicates the performance, normally like congestion or queues, all the fuel consumptions, or the collision type of performance. So the lower the better, right? So the left side is our algorithm, and the right two are the commonly used today in practice. You can see that we consistently lower. So the middle in the second row is actually safety. There's some kind of, the reason we are lower because the parameter was set very unrealistically. But I can talk more if we have time, but I skip that. So the right side is for different penetration, how the performance look like, right? So the general trend is our algorithm is consistently better, and with more penetration, the performance improves, largely. That's sort of the general conclusion. So, well, with this, the Mcity's help with the Mcity 2.0, we were able to conduct this field testing, and the good news is shows consistent results with our simulation study, right? So we actually did the demo in July for international conference, and we wrap up this, and this will be presented at the coming Transportation Research Board annual meeting in January. We are trying to hopefully to work more with Mcity to test, to sort of expand the research to so-called multimodal, consider like buses, trucks, but more importantly, other users like pedestrians and bicyclists, and consider performance not only mobility safety, but also like equity aspects into the evaluation. So this is what my students are actively working on right now. So, and also to a large network. So that's sort of the what I like to share at this moment. Yeah, so that's it. Oh, yeah, thank you. I think the next will be the live demo. Yeah.
Okay, so on the left side, we have the Foxglove application, which will show us part of the Mcity network. The intersection that is going to be controlled using the multi-scale SVTC algorithm is one on the upper left side of the network, or the one that I'm pointing at using my cursor. On the extreme left side, we can also see some other information on the physical vehicle on the field, such as its current and targeted speed. And on the top right side of the screen, we can also see some other information, such as the speed difference between the target vehicle and the nearest leading vehicle, as well as information on the latency between the two sides, which is the latency between our system in University of Washington in Seattle and the Mcity facilities in Michigan. On the bottom right side of the screen, we can also see the cameras on the field that will get updated as the vehicle moves through the network. So what's going on here is that at each 0.5 seconds in time, the SVCC algorithm is collecting the current state, the information on the current state of the target intersection, which includes the current signal phase, as well as the current speed and position of vehicles that are incoming into the intersection. Using this collected information and based on a model predictive control scheme, then the multi-scale SVCC algorithm calculates the optimized signal timing plan and also optimize vehicle trajectories for the next prediction horizon in a way that it would maximize the overall vehicle throughput into the intersection and also minimizes the overall delay as well as vehicle fuel consumption. So for example, here at this moment, instead of going through a cycle-based signal phasing, like what fixed time and actuated signal phasing plans do, the SVCC algorithm decided to turn this particular phase green immediately because this would eventually result in an overall better performance at the intersection. Yes. Yeah, so after the run is finished, the output data will immediately be sent to us from the Mcity side and can just get access to all sorts of information, such as the information on the conflicts, the amount of emission that the vehicles produce, and also information on the trip info for each vehicle at each time step, with which we can run our analysis on evaluation of the SVCC algorithm and see how it outperforms other conventional signal phasing plans, such as fixed and actuated signal phasing.
Great. Thank you, Sakiba. Sakiba, please say hi to the room of people here.
Hello, everyone.
Yeah. So you've been working on this for the last couple months, but you never get a chance to travel to Michigan. So maybe next time.
Yes, hopefully. Thank you.
I would say it's terrible weather, but she can see, so she knows I'm lying. Yeah. Questions? Let me get a mic to you so she can hear you too.
Thank you, Greg. Thank you, Jeff. So I have a question. Can you comment on what is the major difference between you purely simulate that AV versus you involve a vehicle in the loop in terms of behavior or outcome you would see? So what is the major difference you would see? What's the benefit, basically?
So I want to answer into two aspects. For the Mcity 2.0 facility, I was told there's almost no difference because they are trying to, the CVs are exactly the same as real CVs. But in real testing, if you go to the streets, I think there's driving behaviors might be different from the actual vehicles on the street and also the CVs. So the traffic infrastructure might be different. But again, in this, because we are doing a controlled environment, so everything is a digital twin format, so it's supposed to be very close to each other. So that's my sort of understanding. Yeah.
Really great work. So I have a question. So what do you think, can you comment on what is the kind of latency or the general kind of network requirements or the application level requirement about how long you had to get in the data before you're making some decision, right, change the lights, and how much data you're going to expect to coming from the real world?
Definitely. I think Derek sort of showed some sort of latency parameters. From our testing, so normally it's, I think one of the sort of dashboard shows the latency data. So normally it's within 50 milliseconds. And our algorithms on the EDOP side, normally, if you give us 100 milliseconds, we should be good to, to run. So I think that's probably, for the testing, right, we have perfect environment, so it works nicely. We haven't seen the issues of latency.
So that was more kind of coming from, if you do the traffic control, you had to synchronize a lot of different intersections.
Yeah.
So what is the ideal kind of time scale you want to make the decision, like once every second you want to change, you actually do it, say, once 5 minutes, whatever stuff, to coordinate all the traffic, right? So it's not just a local intersection, but overall.
I think in our algorithm, the traffic control is okay because it normally run, longer horizon. We run every 5 seconds, but you could probably do longer because don't expect things change that frequently. Vehicle control, we do 0.5 seconds, but you can do even like 100 milliseconds or even quicker, depends on the scenario, right? So if, I guess for real traffic control, like let's say if we wanted to control the, I don't know, couple hundred traffic lights in Ann Arbor, I think this is, maybe the next testing we should experiment, what's the latency requirement and everything, so.
So you can't have a think about integrate with the CV2X, and then you actually send the signal
data,
to the.
Yeah.
Thank you.
Right.
And so if you update your algorithm, and in that time interval, within the 100 milliseconds, they should be able to change it. And in Mcity, we run real controllers, and so it has the capability to control every 100 milliseconds.
But you definitely don't want to change your traffic light every 100 milliseconds. So that's why I'm saying 5 seconds is already fast enough.
Other questions? Okay.
Right.
Thank you both.
Yeah. We'll invite Greg Stevens back.
Yeah, thanks.